Hello, and welcome to Evaluating Functions. My name's Tuesday J. Johnson. I'm an assistant professor at Doña Ana Community College and a lecturer at the University of Texas, El Paso. This lecture is for Intermediate Algebra, Math 120 at Doña Ana Community College, also at Mexico State University, same class. I'm using Intermediate Algebra by Turner and McKeague from XYZ textbooks. This is Chapter 3, Linear Equations in Two Variables and Functions. Section 3.6, all about evaluating functions. And if you need to watch this a couple times, you should, because section 3.7, we're going to need this evaluation process a lot. So first, let's start with function notation. If we let f represent the rule of correspondence defining y as a function of x, then the notation y equals f of x is used to indicate that y is the range value assigned by the function to the domain value x. So the equation y is a function of x, y equals f of x, represents function notation. This is not multiplication. This is a function evaluated at x. So let's start small. If each pair of the following ordered pairs belongs to the function y equals f of x, we can express each pair using function notation. So I have a point xy, 10, comma, 0.1, or 1/10. To write it in function notation, I would say f of x, so f of 10, equals y, and the y value is 0.1. That's it. F of 0.25 equals a half. Don't overthink it. Don't make it harder than it needs to be. If you give number 3 a shot, hit pause. Alright, well, if you came back, hopefully you came back, f of a negative 1/5 equals negative 1/10. That's it. That's all there is to function notation. The input, the x value, the output is the y value. Alright, so let's let f of x be 2x minus 5 and g of x be x squared plus 3x plus 4, and we're going to evaluate. That's what this whole lecture is about, right? So here we go. If I want to find f of 3, I use something called the skeleton method. And the skeleton says, all right, I'm going to take the function f, and I'm going to take out the x. And everywhere there was an x, I'm going to put in parentheses. This is the structure or the skeleton of the function, right? The fleshy stuff we'll deal with later. This is just the structure. Then we put in the fleshy stuff. I want f of 3, so everywhere I have an open set of parentheses, I replace it with a 3, both on the left side of the equal sign and the right side of the equal sign. So f of 3 is 2 times 3 minus 5. 2 times 3 is 6. 6 minus 5 is 1. That's it. Starting with a skeleton form, it's easy to evaluate a function. So let's find g of negative 2. I start with the skeleton of g. G of something equals something squared plus 3 times something plus 4. And we can see up here in the definition that, quote, something is an x. In the skeleton, in place of something, in place of x, I put in parentheses. But once I substitute, I want to find g of negative 2. I'll put negative 2 everywhere I have an open set of parentheses, which is every place I had an x. Order of operations says negative 2 squared. That's negative 2 times negative 2 is 4. 3 times negative 2 is negative 6. Don't forget the plus 4 hanging out the back. 4 and 4 make 8. And then if I subtract 6, 2 is what remains. So g of negative 2 is equal to 2. Let's do another one for g. G of negative 3, I start with my skeleton. Something squared plus 3 times something plus 4. Right? Up here it's x. Up here we're just going to have parentheses. When we substitute the negative 3, that's negative 3 squared plus 3 times negative 3 plus 4. Negative 3 squared is 9. 3 times negative 3 is negative 9 plus 4. Well, the 9's cancel out, and I'm left with 4. G of negative 3 is equal to 4. Don't overthink this one. Remember, x is called a variable. It varies. What if I wanted to find f of a? Well, f has a form, right, a skeleton of f of something equals 2 times something minus 5. In this case, the something is an a. So in place of the parentheses, inside the parentheses I put an a, and when I simplify there's nothing to combine. It's just 2a minus 5. It's just a different variable for our function. F of x equals 2x minus 5, f of a is 2a minus 5. Do not overthink it. But let's make it harder. F of x plus h. So we can evaluate at a number, like we did in the first 3 examples. We can evaluate at a different variable, like we did in example 4. Or we could evaluate a function at an expression, like we are here in number 5. But for me, it always starts the same. I'm looking at the function f. I want to write the skeleton of f. Inside this skeleton, I take out the x's, I put in the parentheses, right, the structure. And then I substitute. The x plus h goes in my parentheses on the left, so x plus h goes in the parentheses on the right. To simplify this, I'm going to simply distribute the 2. 2 times x, 2 times h, and don't forget the minus 5 hanging out the back. We can also evaluate functions if we're given information in a table. Maybe we're not given the algebraic representation, the formula, but if we have the numeric representation in a table, we're still good to go. So for the given table of values, if y equals f of x, and I wanted to find f of negative 3, well, on the inside, the input, the domain value, is an x value of negative 3. So I find an x value of negative 3. The y value that goes with that is 4. Y is the same as the output of the function, so f of negative 3 equals 4 in function notation. If I want to find f of 1, when x is 1, I go to my table. My y value is negative 1. So I can rewrite this. F of 1 is equal to the y value negative 1. Let's make it more challenging. 5 times f of 0. Let's ignore this 5 for right now. When x is 0, my y value is negative 2. So 5 times f of 0 is 5 times negative 2, which gives me negative 10. This is multiplication, whereas f of 0 is evaluating a function. It's all in context. Make sure you understand the context of the problem in order to appropriately answer it. Continuing, number 4, we're going to make it even harder. 2 times f of negative 2 minus 3 times f of negative 1. Let's use a highlighter here. If I start with f of negative 2, I'm going to take negative 2 and find my y value, which is 5. Then I'm going to find f of 1. I use my x value of 1 and find my y value of negative 1. I can put these together. I want to find 2 times f of negative 2 minus 3 times f of 1. So that's 2 times 5 minus 3 times negative 1. 10 plus 3 makes 13. All right, a real quick definition. The graph of a function, y equals f of x, is the set of all points in the plane, x comma f of x, right? So x comma y, like we've seen before, where x is an element of the domain, and f of x is the corresponding element from the range. So we're going to evaluate some functions using the graph. Use the graphs of y equals f of x and y equals g of x as shown to find the values of f and g. So let's see. F of 0. Here's a graph of f. When x is 0, my y value has a height of 1. Don't overthink it. Don't make it harder than that. When I'm looking at f of negative 3, I go to an x value of negative 3, my y value right here, also 1. Looks like I picked some bad examples. What would you say that f of 1 is? Well, f of 1 right here has a y value of 0. Little bonus example there for you. In the graph of g, all right, if I want to find g of 3, here's 3. My y value is a 3 as well. See how I did in this example. An x value of negative 1, my y value will be negative 2. So this tells me the x value, And this is the corresponding y value that we come to in evaluating the graph. Let's look at a word problem. Everybody loves word problems. The linear function s of x equals 1.4x gives the amount of stretch in a specific spring, s of x, in centimeters. All right, so the amount of stretch is in centimeters when a weight of x pounds is added to the spring. So if I'm given something in pounds, it's x. If I'm given a length, it's s of x, right, in centimeters. So how much will the spring stretch? How much will the spring stretch? Oh, find s of x if a weight of 2.5 pounds is added. 2.5 pounds is an x value of 2.5. Okay, I could find s of 2.5 by everywhere I see an x, I'm going to replace it with 2.5. 1.4 times x in the original function, 1.4 times 2.5 for this specific example. 1.4 times 2.5 is 3.5 centimeters of stretch with that weight. But in the same situation, what amount of weight, that's a fancy way of saying find x, will cause the spring to stretch 5.6 centimeters? If the stretch is 5.6 centimeters, we want to find the x value that makes that happen. So I'm going to replace this s of x, right? The amount of stretch, all of s of x, is replaced by the 5.6. I don't know my x. I want to find x. So 5.6 equals 1.4x. If we divide both sides by 1.4, we'll find that x has to be 4 pounds. 4 pounds on this particular spring makes it stretch 5.6 centimeters. Evaluating functions algebraically, numerically, and graphically. Don't forget a little bit of word problem action here. Thanks for listening.